Hi, this is Thomas. Welcome to math class. Today's topic is the Theorem of Pythagoras. The Theorem of Pythagoras deals with right triangles, so we have applications in geometry. We're going to be using algebra, and in later content we'll see that the Theorem of Pythagoras is relevant to trigonometry as well. We'll begin with stating the theorem. The theorem is the equation a squared plus b squared equals c squared. And these are the sides of a right triangle. A and B are the legs, which are, I'll label in this example A and B, which are the sides that form the right angle, and C is the hypotenuse. So in a basic application of the Pythagorean theorem, if we are given a triangle that we know is a right triangle with side lengths of 6, and let's say one leg is 6 and the hypotenuse is 10, then we can use the Pythagorean theorem to solve for the missing leg length b. A squared plus b squared equals c squared. In our case, we have two values. 6 squared plus b squared, we want to solve for b, equals 10 squared, which ends up as 36 plus b squared equals 100. And we can continue. B squared equals 100 minus 36 by subtracting 36 from both sides, which is equal to 64. And now I'll take the square root of both sides to get to b equals. In typical algebra, our answer is plus or minus the square root of 64, which is 8. But in the case of our calculation, anytime we're using the Pythagorean theorem, we're calculating the length of the side of a triangle, so we only want the positive value, and we will always keep this in mind. So instead of considering the positive and negative options, we're only going to look at the positive option. So here the side length is 8 using the Pythagorean theorem. Now we're going to look at two particular types of right triangles. One type, Pythagorean triples. A Pythagorean triple is when all three side lengths are integers. One example is the solution we just completed. The sides are 6, 8, and 10. Those are all integer values, and this is one example of a Pythagorean triple. The most common Pythagorean triples are 3, 4, 5, and 5, 12, 13, and 8, 15, 17. If you were to test these to see if they work in the Pythagorean theorem, in the equation, you can use the large numbers for the value of c, the other two numbers for the values of a and b, and they will all result in true equations, a squared plus b squared equals c squared. If you were, on the other hand, to try the three values, let's take 8, 15, and 18, then those will not result in a true equation. 8 squared plus 15 squared is not 18 squared, so those are not possible side lengths for a right triangle. There are many combinations of side lengths which aren't integers. If you do have side lengths and all three measurements are integers, you have a Pythagorean triple. Notice that our first item in the list, the 3, 4, 5, a multiple of the 3, 4, 5, if we multiply each of those by 2, we get 6, 8, 10. And that's the example that we worked, our first example, on the left side of the screen. Let's look at a second particular type of right triangle. I'm going to refer to these as specials, and there are two. So we've considered triples, And now let's look at specials. First is the 30, 60, 90 right triangle, and second is the 45, 45, 90 right triangle, referencing the angle measures of the triangle. 30 and 60 with our remaining angle as our right triangle, our remaining angle is 90. And in the second case, 45 and 45 with our remaining angle as 90. The sides have particular relationships among one another in these two cases. So starting with the 30, 60, 90, the short side, which is opposite the smallest angle, as is in the case with all triangles, the shortest side is always opposite the smallest angle. We will label that side length x. And the longer leg is x times the square root of 3, and the hypotenuse is 2x. In the case of the 45, 45, 90, the two legs are the same length as their opposite two equal angles, and we will label those lengths x and x. And the hypotenuse is x times the square root of 2. So with both the triples as well as with the specials, if you know some information about the triangle, you can calculate lengths without using the Pythagorean theorem. If, for example, I'm given a triangle and I know that the legs, I know it's a right triangle, and I know that the legs are 10 and 24. Now, I could use the Pythagorean theorem to solve for the length of the hypotenuse, but I might also notice that 10 and 24 are multiples of 5 and 12. 5 times 2 is 10, 12 times 2 is 24, and if I can associate, if I identify these values with the 5 and 12 of the 5, 12, 13 triple, then I know that my hypotenuse is 13 times 2 because 10 is 5 times 2 and 24 is 12 times 2. 13 times 2 is 26. I didn't need to use the Pythagorean theorem to calculate that length. Another example, if I'm given a right triangle and I know that one of the angles is 60 degrees and one of the legs is 5, and I'm asked to calculate the value of the hypotenuse, which I'll label as C, then I can, if I understand the specials, the 30, 60, 90 special, I can determine the value of C without using the Pythagorean theorem. This is knowing that one angle is 90 and one angle is 60. I know I have a 30, 60, 90 triangle. Even without the 30-degree angle being labeled, I can use my triangle properties to determine this is a 30, 60, 90 triangle. And I know the relationship between the short leg and the hypotenuse is x to 2x. And I have the short leg of 5, and I need the hypotenuse, which I've labeled as C. So I will replace my x with 5, and to get to a relationship x to 2x, I will multiply 5 by 2, and my hypotenuse is 10. C equals 10. And again, I was able to calculate the length of one side of the right triangle without using the Pythagorean theorem. So in this video, we've learned the theorem of Pythagoras. We've seen particular cases of right triangles that we're calling triples and specials. And in the next video, we're going to look at applications of the Pythagorean theorem for problem solving. I'll see you then.